All right, this is homework number 29. And we won't be sketching graphs for our AP test, but it's kind of a good thing to start parametrics with just understanding how parametric equations relate to regular rectangular equations. So that's why we're going through this assignment here. Sketch the curve represented by the parametric equations. Include the orientation of the curve. Write the corresponding rectangular equation by eliminating the parameter. So that means get rid of t or theta. I think those are the only two parameters they usually use. And have everything in terms of x and y. So start with sketching the curve. Now, I'm just going to do a few values for t, and I'm just going to pick values 0, maybe through 3. T can be negative. So when I say that I'm only going 0 to 3, I'm not getting a full picture. If I do negatives as well, the curve could continue on. But like I said, we're not going to have to graph these by hand for any reason for our AP test that I can think of. So I just don't want to spend a huge chunk of time getting this giant graph here. So, okay, so if we plug 0 in for t into the x equation, we get negative 3. Plug 0 in for t in the y equation, we get 1. So the first point on our graph is negative 3, 1. So that's at t equals 0. And then when you plug in 1, you get 2 minus 3 is negative 1. 3 plus 1 is 4. So negative 1, 4. And then plug in 2. 4 minus 3 is 1. 6 plus 1 is 7. So 1, 7. And then plug in 3. 6 minus 3 is 3. 9 plus 1 is 10. All right, so these points are forming a line. I can connect them with a line. It will continue on from there. And when it says indicate orientation of the curve, they just mean show arrows that indicate in which direction you're going. All right, so I should be able to get some sort of a linear equation if I eliminate the parameter. So for these two equations, it's easy to isolate the t, so I'm going to do that. So x plus 3 could equal 2t, and then x plus 3 over 2 could equal t. In the other equation, y minus 1 could equal 3t, and then y minus 1 divided by 3 could equal t. If both of these equations are equal to t, I can set them equal to each other. Oops. Try to write them down correctly there. And there's not really a rule for how far to simplify this. I'm going to go ahead and multiply the 3 to the other side and the 2 to the other side. So it'd be like 3x plus 6 equals 2y minus 2. And I don't know, I'm trying to get a linear equation, so maybe I'll just get my x's and y's on the same side, kind of like a general form equation. And I can subtract, oh wait, this is an x plus 3. Sorry. X plus 3, that makes this a 3x plus 9 when I multiply by 3. There we go. When I subtract 9, I get minus 11. So I'm going to call that my rectangular equation. You could have solved it for y. I think you could probably even just leave it back here. But if we were doing something like this, I bet we would be looking for a multiple choice answer, so we'd probably have to manipulate it a bit. All right, take a look at number 8. You can see I did a little graphing in Desmos on this one because, again, if I'm not going to plug in zeros, I might not get the full picture here. So let's see what we do get. So start with t, x, and y. I'm just going to plug in 0 through 3 again. I think that'll give us a decent start to a picture. So if I plug in 0, I get 0, 0. If I plug in 1, 1 plus 1 is 2. 1 minus 1 is 0. Plug in 2. 4 plus 2 is 6. 4 minus 2 is 4. 9 plus 3 is 12. 9 minus 3 is 6. Now, if I plot these points, 0, 0, and then 2, 0, I might be interested in like what is this point? Like, is the graph going to go up between those two or down? Let me plot the rest of the points first. So 6, 4, and 12, that's like out here somewhere. 6. I'm kind of it's kind of hard to get this in the correct orientation. I'm really not doing that correctly. It's supposed to kind of swoop up, we can see. So, okay, so 12, 6, I'll just kind of estimate that, I don't know, to be about here. Or no, I guess, do I have something wrong here? 6, 4. Oh, it's not 6, 4. That's why that's being so weird. It's early. Sorry. When I plug in 2, I get 4 minus 2 is 2. There we go. 6, 2. See, I knew something was going wrong. Okay, so then 12, 6. That seems a bit more reasonable and in line. All right, so what can I plug in? Well, I went from t equals 0 to 1, so maybe I'll check out what if t equals 1/2. It's allowed to equal a fraction. I just want to know, is the y coordinate positive or negative? So the y coordinate, I guess I could check the x coordinate too, but the y coordinate would come out to 1/4 minus 1/2. That's negative 1/4. So that tells me that like somewhere in here, the graph does dip below. So it's going to do one of these little swoop type things. And I'll put in my little indication arrows, and I can see that I just graphed like this piece here. So if I would have put in negatives, t less than 0, I would get this side of the graph. And if I put in, excuse me, t's between, like my fractions, t's between negative 1 to 1, and then I would get this little section down here. What about taking care of the equation? So there are probably a few different ways to do this, but I cannot just simply isolate the t for this one. But both of these look like they're almost perfect square trinomials. So we're going to have to pull an old trick out of our bag here, which is complete the square. So complete the square is how you create something that you can factor and then square root to isolate. So complete the square is taking the value in front of the linear term, the b, dividing it by 2, so 1/2, squaring it, which is 1/4. And I can do that legally as long as I add that to both sides of my equation. And then how does that help me? It makes it x plus 1/4 equals t plus 1/2 squared, right? This is how complete the square works. It's been a while since we had to do this. And then if I were solving for t, which I can now do because it's only in one place, I can square root both sides, which would generate a plus or minus. And I can subtract 1/2. So this is one solution for t. We need to do the same thing for y as well. So leave a little space to complete the square. T squared minus t. You're still going to add 1/4 to both sides. And that's going to make this so we can factor this into t minus 1/2 squared. And then we can square root. Plus or minus the square root of y plus 1/4 equals t minus 1/2. So 1/2 plus or minus the square root of y plus 1/4 is equal to t. Those two equations can get set equal to each other. So negative 1/2 plus or minus square root of x plus 1/4 can equal positive 1/2, excuse me, plus or minus the square root of y plus 1/4. I can get the 1/2s on the same side. If I add 1/2 over here, I get 1. And this is plus or minus, so whether I add or subtract it, I can move it over to this side. So plus or minus the square root of x plus 1/4 plus or minus the square root of y plus 1/4 is equal to 1. So in Desmos, I'm not going to take the time to do it right now, but in Desmos, I typed in all four combinations of this, both positives, both negatives, one positive, one negative, alternating. And that's how I got the full graph for that. All right. Let's take a look at number 14. So this says x equals the absolute value of t minus 1 and y equals t plus 2. So let's get that graph first. And just keep plugging in 0 through 3. When I put in 0, I get the absolute value of negative 1, which is 1. 0 plus 2 is 2. 1 minus 1 is 0. 1 plus 2 is 3. 2 minus 1 is 1. 2 plus 2 is 4. 3 minus 1 is 2. 3 plus 2 is 5. So let's plot these points first. So 1, 2, 0, 3, 1, 4, 2, 5. So it's sort of we're getting like this sideways absolute value graph. If we plugged in negative values for t, we would get more of it going this way. So how do I eliminate this parameter? Now with an absolute value equation, remember when we solve absolute value equations, we normally say there's a plus or minus involved somewhere, and you can put it wherever. Like I think when I first did this, I said x equals plus or minus t minus 1, but you can also put the plus or minus on the x side. So you could also say, okay, but plus or minus x could equal t minus 1. So you don't really need this necessarily, but let's just say we skip to here. And then you could solve for t. You could say, we'll just add 1 to the side. 1 plus or minus x is equal to t. And then on the y side, y is just t plus 2, so we don't have to do all that fancy stuff. We just, y minus 2 is t, and I can set these equal to each other. So 1 plus or minus x is equal to y minus 2. Now, use the graph to inform you. That's the other reason they're having us graph this. We should know that an absolute value graph that's opening sideways, it means that the absolute value needs to be around the y, and this one's been shifted a bit. So when I have plus or minus x, I want to isolate that. Plus or minus x is equal to y minus 3 if I subtract this one over. And then just like I did before, the plus or minus x means there could have been an absolute value around the y minus 3. So just like I did from here to here. Because that's what you do when you are setting up, when you're solving an absolute value equation, you break it into two equations. One's positive and one's negative. All right, so I'm going to leave this like this. For the next section, it says use a graphing utility to graph the curve represented by the parametric equations. So you could do this two ways. You don't have to do this for the AP test, but you could switch your calculator into parametric mode. So go to mode. We're normally in function mode, but you could switch to parametric mode. We also have polar mode and sequence mode, but again, you don't have to use any of these. You should not switch modes for your AP test. It needs to be in function mode to be able to solve by graphing and things like that. But anyway, just to show you this. So let me get some of this out of here. So I could just graph these two equations. It's not going to put in a theta, but I'll type in 6 cosine, make sure you're in radian mode, to, if I type what's normally x, it's going to show up as t in parametric mode. If you're in polar mode, it'll type in theta, and if you're in sequence mode, it'll type in n. That's why those other ones are there. Y is 4 cosine of 2x. So let's just like zoom 6. Oh, wait. Maybe not. Let's see. I guess zoom 6 is probably not what I want for this, is it? Let me see if there's a better option. You know what? I don't know. Let me see what it was. Let me reset here. Let me see what it was by default. Sorry about that. Let me switch to, I must have just hit graph before, I guess. So if I switch to parametric mode, what is the window? Oh, okay. So they go 0 to 2 pi, and they're counting by something. So I will not mess with zoom 6, I guess. Okay, now we know. Like I said, I don't switch to this mode very often because we don't do this on our AP test. So just haven't worked with it a lot. So I'm just going to press graph. Oh, there we go. Okay, so this looks like an ellipse, right? So here it is here. I have the window zoomed strangely. So when I get rid of the parameter, which in this case is theta, then I should have an ellipse equation. Now, what I'm going to do when there are sines and cosines involved, remember we have this identity that says sine squared theta plus cosine squared theta equals 1. This is the Pythagorean identity. Now, this is true for if these angles match, this is true. So I could say sine squared of u plus cosine squared of u. Anything that matches is equal to 1. So the fact that these are both sine 2 theta and cosine 2 theta, I can still use this identity. But first I need to divide by 6. Get the trig part by itself. And divide by 4. All right, and then like I said, sine squared theta plus cosine squared theta is equal to 1. Sine squared would be x squared over 36 plus cosine squared would be y squared over 16. And that's equal to 1. Again, it's probably been a couple of years since you did conic sections, but this is an equation for an ellipse rather than a circle, because if you get rid of these denominators, you wouldn't have just x squared plus y squared equals a radius squared. These are different denominators. All right, let's take a look at 32. So let's just graph it like they were saying. So this one is e to the 2x and just e to the t, I should say. Just press graph. Maybe that's like a square root type function. All right, so how do I eliminate parameters on this one? So we want to solve for t, and t isn't an exponent. So the inverse of an exponential function is 2 log, or in this case, natural log, both sides. Because remember, the natural log of e to the 2t is just 2t. So the natural log of x equals 2t. Natural log of x divided by 2 is equal to t. Over here, the natural log of y equals the natural log of e to the t, which just means t equals the natural log of y. I can set those equal to each other. I want to get rid of the natural logs, but before I can do that, which would mean I need to write both sides as base e, but before I can do that, I need to get rid of this divided by 2. So now remember, this is the same as like having a 1/2 out in front. And if you have a 1/2 or any number out in front of a log, you can make that an exponent. So this is the natural log of x to the 1/2 is equal to the natural log of y. And then that, or square root of x if you want to write it like that. So when I base e both sides, I'm going to be left with x to the 1/2, or square root of x, equals y. Now there is sort of a caveat here. My graph looks like it's starting at 1, 1. And maybe it is, let's see, because we can't, are we ever going to be able to get x equals 0 for this? I don't think so, right? Even if we plug in negative t's or positive t's, we're never going to get e to the 2t or e to the t to equal 0. So that's not possible. So I'm just going to say x needs to stay greater than 0. You could also say y greater than 0. Now it could be, I think that we could get fractions. It's just that this graphing calculator is not getting in close enough. But if I have a really small value for t, like negative something, then it's going to be very, like negative 1 million for t or something. That's going to be really close to 0, but not quite. So I think the calculator just can't get pixelated in there. All right, let's see. Eliminate the parameter and obtain the standard form rectangular equation. So we're supposed to be getting a circle out of this. They're telling us that. And I kind of see pieces of a circle equation. So what I did for this one was, again, try to isolate just the cosine or the sine like I did earlier. So that would be x minus h, and then you would divide by r to get cosine by itself. And then y minus k, again, divided by r, would get sine by itself. And then we can use our same relationship, cosine squared plus sine squared equals 1. So that means you're squaring x minus h over r, and you're squaring y minus k over r, and that's equal to 1. And then to separate that out a bit, that would be x minus h squared over r squared plus y minus k squared over r squared equals 1. So because I have the same denominator here, if I multiply everything by r squared, then I get x minus h squared plus y minus k squared equals r squared. And that is the equation for a circle with a center hk and a radius length r. Find two different sets of parametric equations for the rectangular equation. So this is kind of weird. I'm not really doing anything very exciting here, but it's just a parametric equation could just be basically just like think of something you can set x equal to and then make y equal to that expression. So like, for example, the most basic one could be, let's just make x a t. So x's parametric equation is t, and y's is just 6t minus 5, right? That would get me y equals 6x minus 5, and it would generate a graph that has the same line. Another thing that we've been doing pretty commonly is x could be equal to either sine or cosine, so I think I chose cosine theta. And then y could still be, instead of 6x minus 5, it could be 6 cosine theta minus 5. So those are kind of silly examples. I'm sure there are more complicated examples, but again, this is not really something, none of this stuff is what we're going to be required to do for the AP test. We're going to be building on these skills. We're just sort of getting familiar a little bit with working with these parametric equations. Okay, which brings me to the true or false section. We were supposed to do through 73, but then I guess 73 must have been on the next page, which didn't make it into my PDF, so I just said, forget about it. All right, so 71 and 72. These could be kind of tricky too. So true or false, the graph of the parametric equations x equals t squared and y equals t squared is the line y equals x. Now we're really splitting hairs here with vocabulary. They said the line y equals x. Now it is true that, like, sure, t squared equals t squared. That checks out. So that substitution makes sense. But will we get a full line on a graph? Like, will we get this line as we go through this? So let's check. This time, let's go ahead and check. Actually, let me leave that on. Shoot. This is the line, y equals x. Let's do a quick little chart where we do pick some negative t values just to be sure. X, y. So I'm going to go like, let's say -2 to +2. So if I put in -2, x comes out to 4, and so does y. If I put in -1, x comes out to 1, and so does y. If I put in 0, 0, 0. Put in 1, 1, 1, 2, 2. So plot those points. Here's 4, 4. Here's 1, 1. Here's 0, 0. My line's supposed to be going through that. And then I'm back to 1, 1, and, 4, 4. And 4, 4 again. So see how we can never get, if x is t squared, x is always greater than 0, and y will always, or equal to, y will always be greater than or equal to 0. We'll never get this section of the line. So the only thing that we actually have a ray, y equals x. So again, we're splitting hairs. It gives the relationship y equals x, but it's not going to be a full line. So this is false. All right, 72, if y is a function of t and x is a function of t, that just means y and x are equal to some expression that relates t, then y is a function of x. That means y is a function of x means if you graphed it, it would pass vertical line test, or more formally, every input has exactly one output. So I was trying to think of a counter example for this because it seems like we can come up with things that maybe would fail the vertical line test. So I was trying to think of like a sideways parabola for this one. This is not the only counter example, but I'm trying to think of like what could my parametric equations be that give me like a y squared. So We could go to x just being t, but then if y is equal to, say, the square root of t, when you solve that for t, you get y squared equals t. And then you put those together to eliminate the parameter, and x equals y squared. And this is not a function because its graph would be one of these parabolas that open sideways. So this is not a function. It doesn't mean you can't do it. An ellipse is not a function either, and we just did an ellipse. But the question was, true or false, will y always be a function of x, just because the other two were functions on their own rights of t, and that's not true. All right, we're stopping there for this assignment. We will get into more of what we're doing on the AP test in the next few days.